So hello Internet and welcome to Space Chile. Our guest today is Hugh Osborn, a postdoctoral researcher at MIT. So welcome Hugh.
Thanks, yeah, it's a pleasure to be here.
Could you introduce yourself a little bit?
Sure, yeah, so I'm Hugh Osborn. I'm originally British, as my accent obviously reveals. I did my PhD in the UK after doing undergrad in London, and then moved to France, where I met you, in fact. And then, so now I'm a postdoc at the University of Bern and MIT, in fact, but I'm doing the stage in MIT right now.
All right, and so you're studying exoplanets, right?
Yeah, that's right, yeah, I'm hunting for planets around other stars.
Nice. So that's what we're going to talk about today, exoplanets. I'd like to start with a little bit of history. When was the first planet orbiting another star discovered?
Sure, so I mean, people have been searching for planets around other stars for a long time. You know, you can go back to the 19th century, and there's this guy called Captain William Jacob who thought he found an exoplanet by studying the stars in the sky and seeing one move around subtly, and thinking there was a planet that was causing that effect. It turned out to not be the case. I mean, in 1850s, there were no planets discovered, but there was this desire to start searching for planets around other stars. Because we have 8 planets in our solar system, and we expect that those dots we see in the night sky also have planets like our own around them. So up until the early 90s, this was kind of out of the realms of technological possibility, mostly because the stars we see in the night sky are so far away that actually detecting directly the light from a planet is almost impossible. You know, if you were to hold the Earth and the sun in the palm of your hands, the nearest star is about 10 miles away, right? Wow. So imagine trying to spot something this far apart that's 10 miles away, right? You're going to really struggle. And actually, most of the stars that we see in the night sky, they are, on that scale, 1,000 miles away. So it's even harder. You know, there's this classic expression we use in exoplanets. It's like trying to spot a firefly next to a spotlight that's hundreds of miles away, and it's basically how difficult it is to find planets. So it didn't happen for a long time, but until in the early 90s, when suddenly, with engineering and technological development, 51 Peg was discovered around a nearby sun-like star. So because planets themselves are so faint and hard to spot next to their bright stars, we tend to not be able to find them directly. We tend to, except in very, very special cases, not be able to see the light coming from the planet themselves. So we have to use an indirect technique to find these planets. We have to look at the light that's coming from the stars they orbit, and using, splitting up that light or using it in a special way, we find the influence of the planets around that star on the light of the star that we can observe. The first method that was used to detect planets was actually using the influence of a planet's mass on its star. So the gravitational pull of a planet effectively, as it orbits, is pulling and pushing that star around very, very, on small scales, but it's enough because if you have a really, really powerful spectrograph, so this method of splitting the light of a star into multiple colors, really, really fine scale kind of color information, through the Doppler shift of that light, so the same effect that causes a police siren to get decrease or increase in pitch as it goes past, that Doppler shift in kind of the frequency of the light that's coming from a star due to it moving around due to the influence of a planet, we can observe that in the color of the star, and we can figure out how big a planet is going around it, and how long an orbit it is on, and all of these things. So even though we don't see the planet, we can figure out a lot of things about it using this indirect technique. And so this was the first technique that was used starting in the 90s, and in 1995, 51 Pegasi B was discovered by Didier Queloz and Michel Mayor in France, working from the Geneva Observatory. And they were in France, but they are from Geneva anyway.
I see. And they got the Nobel Prize for this discovery, right? Yes.
So 2 years ago, they received the Nobel Prize, and actually I currently work with Didier Queloz, so it's quite weird.
Cool.
Working with a Nobel Prize winner, but it's cool.
Nice. And so, what other methods are used now to discover exoplanets?
Sure. So radial velocities, as we call it, this technique of measuring the push and pull of the starlight, that was the first big method of detecting exoplanets. It was used for well, it's still used to this day, but for the first 10 years, that was really what was driving the new planet detections. Mm-hmm. But starting in the early 2000s, this new technique was used called transits. So exoplanet transits are when the planet itself traverses the star as we look at it, so moves between us and its host star, blocking some of the starlight. And we can see that missing starlight effectively in a shadow on the star by looking at the light from the star over time. So we build up a video of the star over time, and then from that we get a light curve, which is how the light coming from the star varies over time, and there's a dip in that light curve where you see a planet passing between you and the star. And by studying that dip, you can figure out, once again, the size of the planet. The bigger the planet is, the more light it blocks. And the orbital period, because we see this dip repeating every 5 days, we know the planet must be on a 5-day orbit. And that became the dominant technique for detecting planets starting in the early 2000s. And then there are these two other methods called microlensing and direct imaging. And these are kind of they get pushed together into this other category in terms of in exoplanet conferences. And I'm sure everyone in those fields are slightly annoyed by that. But for the moment, they're kind of the minority in terms of the number of planets that have been discovered. So in microlensing, what happens is we can observe the starlight of a distant star as a star system, so a star and a planet pass between us and that distant star. But unlike in the transit technique, what happens here is that you actually get this gravitational lensing effect where due to general relativity, masses effectively can act as lenses to large distances. And so the mass of the planet and the mass of the star going between us and this distant star lends the light from the distant star, and we see that in this long increase in light with like this bump from the distant starlight. And we can use that to interpret what planet is around the star that we don't actually see and we probably won't see again. Whereas direct imaging is kind of finding the fireflies next to spotlights. So we put a big telescope, we shine it, we aim it at a star, and we try to block out as much of the starlight as possible. And in some very rare cases, especially young stars where their planets are still kind of glowing from formation, so they have this very hot glow in the infrared, we can actually observe the planets directly if they're far enough from those stars. So this has been done, I think, in 10 or maybe 12 cases now, where we've actually been able to see the light directly of one of these distant gas giant planets.
So how many exoplanets have been discovered so far?
So at the moment we're, I think, on about 4,500 confirmed planets.
Not bad.
Yeah.
And so it's mainly giant Jovian planets.
Well, yeah, so 10 years ago that was the case. 10 years ago we had maybe only 500 planets. And so at that point most of those planets were these giant planets, as you say, these hot Jupiters, or maybe these Jupiter-like planets found by radial velocities. And those were dominating all the planets we saw. But in the last 10 years, we've been able to push down our detections to more kind of Earth-like planets. Not quite Earth-like yet. We can't detect Earth 2.0 at the moment. But certainly sort of into the Neptune regime, the super-Earth regime, where we're looking at planets that are 2 to 5 times the size of Earth. Those have become the most numerous planet that we've detected so far, these so-called super-Earths. So we don't have a super-Earth in our solar system, so we don't really know what they're like, but they tend to be between 2 and 4 times the radius of Earth, so much larger in radius, and between 5 and 20 times the mass of Earth as well. So in this really weird regime in kind of parameter space that we didn't expect to find planets, and we've been able to find a lot of planets there.
Cool. And so what were the most prolific instruments in discovering exoplanets? Sure.
So 10 years ago, the most prolific instrument would have been the HARPS spectrometer. So this is basically a planet hunting spectrograph on the 3.6 meter telescope in Lucia in Chile. And so this was the workhorse for finding these RV planets, and I think it's found maybe 500 planets that way. But what happened after that is that NASA launched Kepler in 2009. So Kepler was a transit hunting mission, so trying to find the shadow of smaller planets as they pass in front of their stars. So Kepler observed 150,000 stars for more than 4 years, and the amount of data that it was able to send back, and the amount of stars it was observing, it found more than 3,000 planets within those. Wait, is that the case? Let's say more than 2,000. It found more than 2,000 planets within that field of view it was looking at. So since Kepler launched, it was really the driver of this acceleration we see in terms of the number of planets that have been discovered. So that's become the kind of the dominant source of planets. But since then, actually, TESS, another NASA mission, the Transiting Exoplanet Survey Satellite, launched 3 years ago now. And this is a mission that's run out of MIT here in the US, and this mission was basically launched as a successor to Kepler. So it was trying to also use the transit method to find the shadows of these small planets. But instead of looking at this one patch of sky, it's looking at the entire sky, and it's trying to look at brighter stars. And so the prediction are that it should eventually eclipse Kepler in terms of the number of planets detected. At the moment, we're only a couple of years in, so I think there's only couple of hundred planets being confirmed from TESS, but there are more than 2,000 candidates now. So it's likely that in the future, TESS will eventually overtake Kepler in terms of the most important instrument in transiting exoplanet science, I guess.
Right. So we are discovering all these exoplanets, but how do you characterize them? How do you know what they are made of? What are their atmospheres? Can there be life?
Yeah, sure. It's a good question. So initially when we detect a planet, we don't know anything really beyond its size. So we either know how massive it is, or we know how big its radius is. So we can't really do much at that point to say what it's made of and what's in the atmosphere and what it could be like, But what often happens is we will try and observe this planet with an independent technique. And so in the case of all these transiting planets, what we get from the transit, what we get from as it passes in front of the star is its radius. We know how big it is, the cross-section of the planet, basically. And then if we use the radial velocity technique, we can get a mass for the same planet. So there we have a mass and we have a radius. And so at that point, you can put these two together and you can get a density for the planet. And that's like the first order we can do in terms of characterization, because suddenly, we can figure out, okay, for these rocky planets, for example, we can figure out, well, is it denser than the Earth? Does it have a bigger iron core? Or is it lighter than the Earth? Maybe it has a big atmosphere or water on the surface, or a smaller core. There's some degeneracy there. We don't know. It's easy to say that something denser than the Earth must have more dense material, so more iron. But we can't say the same for something lighter than the Earth, because it could be there's lots of things that are lighter than rock. So water or ices or atmosphere, So for these super Earth planets, these very common planets kind of between the Earth and Neptune, there's actually this wide range of compositions they can have. They could be, these really, really puffy balls of gas with a very small core, or they could be these kind of giant, almost rocky terrestrial planets. So the only way really to go in and figure out what's going on in those kind of planets is to do atmospheric characterization. So that's the next kind of level in terms of how we can characterize planets. And it tends to be for these transiting planets, we have what we're able to do is, if you can observe a transit of a planet in front of a star in multiple wavelengths, so in multiple colors, effectively, and you can do that extremely precisely. At that point, you can start to be able to see which of those wavelengths passes through the atmosphere and which of those wavelengths are blocked by the atmosphere. If there's a specific molecule in the atmosphere, for example, water, there are actually wavelengths that water blocks light very, very efficiently. So the starlight effectively gets absorbed by the water in the atmosphere, so the planet appears much larger. And then in another wavelength, the light passes through. So effectively, we can use this differential kind of radius that we get from how much light is being blocked at a particular wavelength, and we can back out from that. Okay, is there water in the atmosphere? Is there methane in the atmosphere? Is there haze? So sometimes we see these slopes as just like in the atmosphere on Earth, we see a blue color because the blue light is being more efficiently scattered into our eyes. We see the same thing in exoplanet atmospheres as well. But for the moment, this technique works. Again, it's easier to do on bigger planets. So we can do this pretty well for hot Jupiters, so these big Jovian, planets like Jupiter very close to their star, because these have the biggest atmospheres. These have, very puffy kind of lots of interesting things in their atmosphere as well. And so for the moment, these are the planets where we have the most information about the atmospheres. But we hope that in the future, with bigger and better space telescopes and with better techniques, we can push this to smaller and smaller planets, and eventually, hopefully, use it to characterize the atmospheres of Earth-like planets in the future.
So that's actually the perfect transition to my next question. So in October this year, NASA will launch one of its more ambitious projects into space, the James-Webb Space Telescope.
Yeah. And
one of its main goals will be the characterization of exoplanets, right?
Yeah, it's going to be incredible. I mean, touch wood that James-Webb launches okay, and it stays on schedule this time. But once, if and when it launches, it's going to do a lot of studies where it will do exactly this. It will look into the atmospheres of exoplanets. It should be one of these instruments where we can start pushing down from this hot Jupiter regime towards studying the atmospheres of super Earths and Neptunes and things like this, which we couldn't do in the past. Mm-hmm. And in fact, James-Webb should be able to detect in a single, one single transit, what Hubble took like 20, 30 different transits to observe. So suddenly we're going to improve the signal we're getting from these planets like amazingly. And so we should start being able to find new atmospheric species, so new molecules in the atmospheres, and potentially even start studying some Earth-like planets.
So let's talk a little bit about your personal work. So you were recently involved in the characterization of an exoplanet system named Lupi.
Yeah.
Is that correct? Yeah. So can you describe this discovery and why it's important?
I mean, Lupi is one of the better names in exoplanets. I mean, most exoplanets are named, HD 137194, mm-hmm. right? So the Lupi, in fact, is named because it is the newest. I don't know where new is in the atmosphere of Greek letters, but it is the within the top 26 brightest stars in the Lupus constellation. So one of the reasons it's really interesting is that it's a naked eye star. So if you go out in the southern hemisphere and you look up into the Lupus constellation, you should be able to see a small dot of light, which is Lupi, the star. And that's actually not really true for many stars that host planets. So the majority of planets that we see on the of those 4,500 confirmed planets, almost all of them are around very faint stars, which we can't see with our eyes, and we sometimes even with a telescope you might not be able to see the star. So that's one of the reasons that the Lupi is a special system. Mm-hmm. So it was discovered to have 3 planets orbiting it, I think 5 years ago now, through the HARP spectrograph. So it was actually first detected using this radial velocity method. Mm-hmm. And they found 3 planets that are in this kind of super-Earth regime, so between about 5 and 10 times the mass of Earth. These kind of multi-planet systems, these are quite common we've been finding relatively many of these systems with multiple planets. What's special about this, and the reason I started to get involved in it, is that I work on a project looking for long period planets in TESS. So looking through the light curves, so the data comes from TESS for all of the stars in the sky, basically, and looking for the transits of planets which happen to transit only once. So instead of you getting these multiple eclipses where the year of these planets, we look for planets that transit once, and then we have to figure out how long an orbital period is through other techniques. And so Lupi was in the list, and there was a moment when I was looking at the light curve and I saw a transit in the light curve. So there was a clear signal of a planet around the system. But at this point, I didn't realize. I just thought it was another star. We have hundreds of these candidates from TESS. But I typed the coordinates into Google effectively, and I saw that this was a known planetary system, right? So this wasn't a candidate. This was a known planet that we were seeing transit. So we already knew how that it was real for one, and that it how big it was, how the mass was, and the light curve that I helped find meant that we could get the radius as well. So suddenly we had, in fact, for 2 planets, there was 2 planets in that light curve. We had really good density for these 2 planets, and so these planets are on, I think, like 10 and 30-day orbits. So they're, as exoplanets go, they're actually relatively long period. Most of the planets we have in that list are less than 10 to 20-day periods. But the 3rd planet in that system is a 110-day period. So this is a really long orbital period as exoplanets go. And it was very unlikely that we would find it transit. So we had seen the inner 2 planets transit, and we just assumed the outer planet would probably not be the case. But so I work with the CHEOPS telescope, which is this Characterizing Exoplanets satellites run out of Switzerland for the European Space Agency, ESA. And so the goal of that satellite is basically to follow up and characterize planets that have been detected by TESS or by other techniques, and to try and improve the radius and find out more about the known planets we have. So we were observing Lupi B and C, so the inner 2 planets with CHEOPS. And at the end of one of the light curves, there was this mysterious extra dip that happened. And it was this really long extra kind of event that looked like a transit, but we weren't sure at first. And then we realized, because we have some idea of what the orbit is from the radial velocities, that actually that orbit predicted perfectly a transit during this time for the outer planet, for this 110-day super-Earth that we didn't expect to find at all. And so we surreptitiously were able to detect this outer planet around a naked eye star on a 100-day orbit. So this will be a really interesting planet to study. And the fact that it's cool, it's only 150 degrees Celsius. So there could well be water in the atmosphere. There could well be things that we find in the Earth, atmosphere, because it's not too dissimilar in terms of temperature.
Nice. And let's dream a little bit. Is there any chance that we will ever visit one of these exoplanets?
Yeah, it's a question I get a lot. And every single time I feel kind of bad that I have to say no, right? Because, we talked earlier about how far away the nearby stars are. If you hold the Earth and the Sun in your palm of your hand, you have to walk 10 miles to get to the nearest star. So that big gulf between the Sun, which gives us life, every energy we have is derived from the Sun, and then there's this massive gulf between it and another star that we could potentially try to get to. It's just too big, and the distance is too great that in a human lifetime, certainly, we would not probably manage to build a craft that could get there and explore. But we can do a lot. I think within our lifetime we'll be able to explore exoplanets from distance. We might be able to start in 50 years start mapping the surfaces of rocky planets around nearby stars. With big telescopes. We won't be able to send a probe, but we'll be able to say if there's continents or life on the surfaces of these planets from afar. And I think that's for me that's enough.